Hello everyone. I'd like to solve problem number 20 for you. It's about the equipotential curves and inferring information based on these curves. We're supposed to look at this figure right here and answer some questions. So before we do that, I just want to explain what's happening here. You have the x and y axis. You have a bunch of contours. Some of them are in red and they have positive values for voltages next to them. The blue ones on this side, they have negative values, and the green one, it just shows you contour of 0 volts. So let's look at the questions. First question says, what is the energy required to move a proton from point A to point B? Okay, so the energy required to move a charged particle in a potential, you know that the potential energy is given by charge multiplied by voltage. Therefore, the energy needed to move a charge, delta U, is equal to Q times delta V. Now, in the case of a proton, we know that Q is plus 1.6 times 10 to minus 19 coulomb, and delta V is the voltage difference between point A and point B. But we already know point A has a voltage of plus 1, and point B belongs to the contour that is plus 3. So going from 1 to 3 is a plus 2. So we know that delta V going from A to B is plus 2 volts. So this is multiplied by plus 2 volts. And the answer is 3.2 times 10 to minus 19 joules. Now, in the problem it says think about the energy units. So since I'm not asking what units you're supposed to use to express your answers, you could pick a unit that works better for you. Now, what you could do when you see that, that's a hint for check which unit of energy will make your answers, will make your life easier. And just use that unit. Unless you're asked to express your answers in joules or electron volt, you have that freedom as long as you use it correctly to pick any units you want. So you can quickly look at all the problems. You see, the first one is asking for a proton. The second one is asking for electron. And then, again, proton. This one is not about a charged particle. Again, electron for energy. Now, here you have plus 1 microcoulomb. So it means that for the most part, we have electron and proton, which both of them have the same charge. They're 1.6 times 10 to minus 19 coulomb. So obviously the better unit to work in is electron volt for those parts at least. So I would recommend then, after seeing this, to actually express your answer for part A in terms of electron volts. And if you look at this, this is basically 1 electron, this is 2 volts, so the answer is 2 electron volts for part A. Well, I didn't name these parts, but let's just go ahead and do that. This is part A, B, C, D, E, F, G, H, I. Okay, now let's answer the next question, and be sure to pause the video and think about it yourself. The next part says, determine the energy change when moving an electron from point B to A. So it says the energy change. That means the potential energy of electron. And note that this time we're going from B to A, not from A to B. Okay, So an electron is going from B to A. So what happens here is, let me write down, so for part B, now we have an electron that's moving from B goes to A. So now what I would do is I would say, okay, again, delta U in this part for part B, again, it's Q delta V, but this time my Q is actually a negative charge. So it's a negative charge. If I want to use joules, I would write it like minus 1.6 times 10 to minus 19 coulomb times delta V. Now my delta V is going from B to A, so my delta V is VA minus VB, which is a negative number now, so this is minus 2 volts. So I get the same answer because this minus sign cancels this minus sign, and I still get plus 3.2 times 10 to minus 19 coulomb, coulomb volt, which is joules. And in electron volt, the answer would still be plus 2 electron volt. Okay, this just shows you that if you flip the charge, so we flipped the charge, but we also flipped the direction, and that's why the minus signs cancel out. Now, the next question, part C, says find the energy needed to move a proton from point E to D. Make sure to pause the video before looking at the solution. So, if you're going from D to E or E to D, doesn't matter. You are moving on the same contour, basically. Now, you could be moving outside of the contour. It doesn't make a difference because electrostatic force, electric force is conservative. So it doesn't matter how you go there, but the point is you're moving from a point to another point with the same voltage. Therefore, you don't really need any energy for that. So the answer to part C is that delta U is 0 because delta V is equal to 0, and this is because point E and D are both on the same voltage contour. Okay? All right. Let's answer the next one. Which points have the weakest, which point or points have the weakest electric field strength? So, looking at this, we know that when you recall that electric field can be quantified as the change of voltage per unit change of distance, basically. Meaning, if you have a lot of change in voltage in a small distance, that indicates a very high electric field. And if you have a small voltage change in a large distance, that indicates a very low electric field. So pause the video and guess which point on this diagram should have the least amount of electric field. So here you see that the contour for plus 1 volt, this contour, is the plus 1 volt contour. This is the 0 volt contour. And then this is the minus 1 contour. So you could see that all the contours are pretty compact. But when it comes to going from minus 1 volt to plus 1 volt, we have a huge space between them. So any points that's located between these two contours has lower electric field compared to other points. So point C, being furthest from the contours, you see here you have the furthest distance between the two contours. and given their values, point C must have the lowest field, and then point F. Well, actually, I'm not going to rank these because this is very qualitative. You would basically answer this as point C and F have the lowest compared to everything else, because it's a bit ambiguous. You have to actually calculate it. But it's not the proximity to the contours, it's more about how compact the contours are, and you see it's pretty open in these two areas, and that's why they have the lowest electric field. Okay, now we're doing part E. Draw the electric field vector at points A, B, D, and E. Okay, now the electric field is perpendicular to the contour, and it points from higher potential to lower potential. Now, if you focus on A, if I want to draw this, I'll use yellow. I have to draw the electric field on this line, perpendicular to the contour. But would I draw it like this, or would I draw it like that? Which one is correct? Well, the electric field has to point towards lower potential, not higher potential. This direction is the direction of increasing potential, so I have to use the opposite direction. So this is the direction for the electric field at point A. Now pause the video and see if you can do the same thing for point B. So I would do something similar for point D. I know that I have to be perpendicular to the contour in the direction of lower potential. Now let's do E. Again, pause the video if you want to think about this for a second and draw it yourself. But the electric field at point E has to be perpendicular to the contour, pointing towards lower potential. Now pay attention here, these contours are negative, so the electric field is actually pointing inwards here, because it's pointing from -1 to -2. How would we do it for point D? Perpendicular to the contour, pointing to lower potential. So you can see that the electric field is coming outwards on the positive sides and is going inwards on the negative side. Part F. Where on the map has the strongest electric field? It may or may not be one of the denoted points. So it's asking you to find the point with the strongest electric field, and it's telling you that it may not be actually one of the points that are already denoted. But what you're looking for is what point on this graph has the tightest, most compact set of contours. Well, as you can see right here, these two contours are very close to each other. What that means is that you have a potential difference of going from -3 to -2. So you have a 1 volt potential difference at that point over a very small distance, which means the electric field is the highest at that point. So you would just circle that point or put a cross to indicate it. Now let's do part G. It's asking if an electron is released from rest, so its initial velocity is 0, at point E, in which direction will it move? Be as specific as possible. So let's find point E. Okay, remember that you already determined the direction of electric field at point E. So the electric field is pointing inwards, as you can see by the yellow arrow. Now pause the video and think, if I put an electron right there, which direction would it fall? If you recall, positive charges would actually flow in the direction of electric field, but negative charges would go opposite. So when the question says be as specific as possible, it means you have to actually draw the arrow and say that this is going to be the direction that the electron is going to move on. Either you can show it with VE, meaning this is the general vector for the general direction of initial velocity of electron, or you could just explain that you've shown it with a vector. But make sure you differentiate between these two vectors. You don't have colors on your test, but that's why we use labels to differentiate these. Okay, now let's do part H. What can you say about the energy needed to move a +1 microcoulomb from point C to point A? C to A. Now, again, we know that, so here now we're trying to solve part H. Okay, so for part H, we know that the change in energy is Q delta V. And we know that the charge, see, when it says what can you say, it means you need to be as specific as possible. And so this means that there should not be any missing information that could be possibly inferred from what's given to you. Given that you already know the value of the charge, it means you need to do some numerical calculation. You know it's from point C to A. So if you knew what the voltage at point C is, you would actually go ahead and calculate it like the previous parts. Now you know what Q is. So you know that your Q is 10 to minus 6 coulomb. It's 1 microcoulomb. It's a positive charge, and it's moving from C to A. So the voltage difference would be VA minus VC. Now you know that VA is +1. So this is 10 to minus 6 coulomb times +1 minus VC. Now the issue here is that you don't actually know VC, and that's the part that is slightly ambiguous, but everything else you had the information for. Now when you look at VC, you see that VC is located between 0, the contour for 0, and the contour for +1 volts, which means that the potential at C must be greater than 0, not equal, greater, because it would have been equal if it was on the green line, and it has to be less than +1 volts. Okay, now if VC was 0, so if you were really on the green line, then this work would be at most, it would be, so VC, let's say VC is 0. I'm gonna actually write it in the next line. So let's consider the scenario where VC is 0, which is not really. We're just trying to look at the extremes of the situation. If VC is 0, then what I get out of here is that delta U, in this case, which I'm going to denote with a 0 there, is going to be 10 to minus 6 joules. If VC is +1, which again it's not, delta U1 would be 0. Now, what this means is that the work done is a number between 0 to 10 to minus 6. So what you can say is that the work done, or the energy needed to move this charge, is delta U is a positive number greater than 0, not equal to 0, and not quite equal to 10 to minus 6 joules. This is the answer. Okay, and part I says propose a configuration of point chargers that could produce equipotential contours similar to what you see, and also explain how it's different. Well, I already gave you some hints when we were talking about this, is that this looks very similar to 2-point charges, where the red contours are similar to what you would see around the positive charge, and the blue contours are what you would see around the negative charge. So this is very similar to having this situation. Let me draw it real quick. This is very similar to having a positive charge sitting there and a negative charge sitting there, and the amount of charges look similar, except it looks like from the graph it looks like the positive charge is slightly the lines around the positive charge are a little bit spaced more. So if I was going to be a little bit more accurate, I would say that Q1 is a little bit, it's similar to, but it's slightly smaller in magnitude compared to the negative charge. Okay, so that's the other, that's the thing, like this looks similar to this. Now, what do the contours look like in this case? They look pretty much like this, and at the midpoint here, you're gonna have a contour that is basically a straight line. And now it's roughly midpoint again. It would be midpoint if the charges were exactly the same, but this would be your V0. And then you should have some contours that surround your charge. So what I would do is I would draw the contour for this one slightly tighter. And then for this one, for plus Q1, I would draw them a little bit wider to convey the information that Q1 charge is slightly smaller than Q2. Now, the question is asking, how does this differ from what we see here? Well, the main thing is that these contours that we have are pretty irregular, and you can see that, like, we have an irregularity here. The shapes are pretty irregular, they're not circular, and so the main difference I would say is that these two, the real contour that we have here in the problem is not actually caused by 2-point charges, even though it's very similar to it. Just because if you had point charges, if you had perfect point charges, you would expect the contours to be pretty circular or elliptical. You would not expect this kind of irregular shape. All right, that was it. Let me know if you have any questions, or if this explanation was not sufficient for the problem. Good luck on your test.